Okay, I think it's time to start. All right, so a couple of things that I wanted to mention before we start with the lecture. A number of you were not able to come today for a number of valid reasons. And they asked me ahead of time of what we're going to cover and so forth, what they need to do. I sent them to the website. So, and I wanted to also show you where all of this information is going to be in case you cannot come, you want to see information ahead of time, or you did not come and then you want to see information after the fact, all right? So a lot of things may happen and then you may not be able to come one day. So what I would suggest in that case that you do is that you go to the website. And so, for example, today, let's assume that somebody wants to see what we did, or it's not everything there yet, but anyways, somebody later today gets on this website and wants to see what we have done. So I would go to week 1. Let's assume that that connects, okay? And then, so every day has its own material, documents. So you see today, for example, we'll do introduction to Top Hat. Then we'll talk about fundamental forces. This is the introductory material to electric and magnetic fields, electromagnetics. And then if you want to see what you have to do, you will go to this that says weekly overview. And it's like in an abbreviated form. But it says what we cover so far. I have to, of course, at the end of today, I'm going to go and upgrade it because a lot of times I put things that I think will do, but there are other things that we have discussed. And then it says here what you have to do. All right, so in case you are not here. I say, of course, a lot more when we are in class. So obviously pay attention to your notes. But for those who have not been able to come, it's this to help. And of course, in addition to that, you will have access to the video, which I have been able to put even for the early. Usually it takes me a few hours to do this, to upgrade, if I don't have another meeting after the class. And like I did this morning, if you go back to the front page, you will see here, it says video for both lectures. That was from Wednesday. And then this is the video for the 8, from the 8 to 8:50. Now, most of the material is identical, but as we make progress with the various topics in this class, it is possible that I will do something in one section and in another is going to be different because of whatever the dynamic is. All right, but under the same kind of umbrella of the material we need to cover. So all of these should help you. And with that, I would like to see if you have any particular questions about this topic. Okay, you can always email me about anything, but just in case it's only about that. So today, going back to our topic, as you will see, first of all, we'll start with an introduction to Top Hat. And we have an example quiz. You remember every Fridays we'll have quizzes. So it's an example. And we are gonna, I'm not gonna give you the solution, but you're gonna see how I'm getting into Top Hat, and you're gonna see what I see, and then also I will activate the example quiz so you can go and check it on your own accounts and make sure that you see the same thing. So not that, excuse me. That is the orientation Top Hat. I have to go one page back. Okay, so here, this is where you get the direct connection to Top Hat. This is your the second one. And that is going to take you to your own section. Make sure that it is your own section, all right, when you connect. I had one student, not too many, last time I taught the class, who for the whole class was solving the problems of the other section. I don't know how was that possible, but that's what I found at the end as I was trying to put grades together. In any case, make sure that doesn't happen because it creates a problem. So you're not going to see that. What you're seeing, so for example, we have quizzes, all right? So I have developed quizzes for this class. So when I go to this quiz, that's how the problem looks like, all right? And before I tell you what you will need to do, I'm gonna activate it later, but I will specifically like to make a few comments about why these vectors that I have put here as a review. So there are a few things that you need to make sure you remember or revisit as we start the material for this class. Vectors, vector properties. Not all of them, there are infinite many, but the fundamental ones. Vector properties, coordinate systems, the various coordinate systems and how they relate. These are important things that you will need to remember for this class. And part 1 in our textbook provides a good review of this. I do not want you to try to memorize everything there now, but keep it in mind that the information, every time you have to deal with a vector-related problem, a coordinate problem or something like that, go and look at the material in the textbook because it's very well prepared, it's very accurate, and then so do not try to go to the web first and then to your book. There are a lot of blogs that you can find through Google. And the material in many of these blogs is either incomplete or inaccurate. So do not go immediately and try to get something without checking its accuracy. But when you go into like credible websites, all right, if it is in a math department, for example, or our math department or something that people do have blogs, but they are graduate students in math, then you know it's gonna be rather impossible to find or rather difficult to find something that is an error. But the primary source for that information is our book. So go there. Now, why is it that I started with vectors before I even consider coordinate systems? Because as you will see today and remember rather, and probably you've talked about that in physics, the entities we will have to deal with in this class, they are characterized not only by their value, but also by direction. All right, so velocity, for example, it's a vector. Because if you say my velocity is like x, 2 meters per second, I get half of the information. The other half is which direction I'm going. All right, so we always, to specific entities, we assign direction. And for us, as you will see next, what we are going to be dealing with, which will be forces and fields. These are entities that need direction. All right, so vectors, of course, the direction implies that we are going to represent those entities with vectors. So remembering things about vectors is very important. Now, why is it important that we know how to sum and subtract vectors? Usually subtraction and summation are the same things. The only thing is that what is the difference between these two, between this entity here and this one. The difference is that vector B, in this case, has flipped its direction. If in the first case, it's like this, going like that, in the second case, it has flipped its direction, it's going like this. But in reality, it's the sum between two vectors, all right? Remember that. So if I were to do it here, I would say, if you have one vector here, A, and another vector here, B, A, and B, the sum of the two is this one. I want you to remember this. Okay. What is the, if without changing this, I would say, if this is A plus B, according to what I said before, what would be A minus B? I would have to take B and flip it. And what is this? Minus B. Agree? And then I will apply the same rule, the same rules. Okay. So sum here, difference here. However, when we get used to this, I don't go all of that. What do I do if I get used to these two, sum and difference? If this is the vector A, and this is vector B, then this is A plus B, and without doing this, I would say this is A minus B. See? So what will this remind you? That they are the two diagonals of a parallelogram. Okay? And why this is that? Because these two, according to vectors, these and these are identical. Okay? So these are the kinds of things you need to remember. Why is this important? Okay. Why is this important? Why do I care about summing two vectors? Because if I have two sources, I am one source, you are another. And we both are charged sources, like we can be antennas, for example, right? That transmit. I create an electric field, electromagnetic field in that case around me. But let's assume that I'm interested in the electric field only. So electric field around me, you create another one. And somebody at the center, you will feel both of them. But what both of them? I mean, is when you say it's both of them, it's very qualitative. You know that both make have an impact. Both contribute to the total field, but you don't know how. And then in that case, you say the person in the middle will feel the sum of the two entities. So to find the total field somewhere, you need to know what are the individual fields that are excited by the various sources, and then you have to add those vectors. That's why summing vectors is so important, okay? You need to remember that. So that particular example is telling you the following. You have to decide which of, for example, there are questions underneath it, and the questions are as follows. So you have to find the right answers by moving them up or down. In that case, I don't want to show it to you because you're going to see the solution. So, but it's going to ask you, it's going to give you a case on the left and a statement on the right, and you have to pair the correct question with the right statement, with the right solution, right? Okay, so usually what I will do in a case like that, I will say here assign homework because it's graded. And when I assign it, you should see it in your accounts. When you go and connect, you should see that. This particular one, I'm going to keep it open until Monday, just before the class. It's an example. You're going to be graded for it. If you just do it without and you're wrong, you're going to get 30 points. If you do it and you're right, you're going to get 60. But it's important because I want you to do it. All right, I want you to find time and to feel comfortable doing that. All right, going and answering this program. And you're graded automatically then in this tool. Any questions about that? All right, we have no questions. So let us then, did you find it before I move on in your account? Perfect. All right, so now let us move away from here. What I'm going to see. There. Okay. And now I'm going to my lectures for today. And since we covered Top Hat, we're going to go and introduce the topic of fundamental forces. Why do I start with forces? How many of you know, are familiar with that topic, with this topic? The fundamental forces in nature, people call it forces of nature, forces of life, forces of the universe. So one of you is, do you have a question down there, you guys? Question? Okay. So you're, I asked the question, I think maybe that's why you raised your hand, that you are familiar with the forces, all right? It's called here forces in nature. How many of you have heard about that? Okay, so, all right, so a few. How many rather have not heard about that? Well, I don't see, I'm not even sure who knows or who does not, but this does not matter. I'm going to review it here. Okay, these are the 4 forces of nature. People call them the forces of life. And I will present them to you. And many places, so if you go, say, and try to find other sources for these forces, you will see them in any particular order, all right? The right order, and I will explain, and of course, electromagnetism is the one that we care about, but they are all connected. And so that's, it is important to see the big picture. So the right order is the one that you see here. And right from which point of view? If we could, which we have not been able to master yet, but if we could understand fully and accurately of how the universe was created from the time of creation, then, and we have so far, we think, as it always happens, every time in history, people think that they know exactly what it is, and then a few years later, you see a revision. But at this moment, we think that we know how the universe was created, not at time exactly 0, but at time t equals 0 plus. So there is a moment, practically people don't know why we were created or how we were created. I mean, we don't know anything that happened at time t equals 0. But I believe on the basis of what we know in physics and chemistry, we know what happened after time t equals 0. And what it means after, I have no idea. I don't think people know. Sometimes they will think it's like a femtosecond. Some other times people will tell you it goes a 1,000 years, a million years. I don't know. It does not matter, all right? Because at that moment in time, time loses its meaning anymore, okay? Because time is a construct that we have created because that's where we live. And for us, time is a measurable entity. We age biologically, and time has a meaning for us. All right, so it's very important. But for the universe, it's another variable. All right, and we don't even know how time it is. Here for us is linear for us, but it's not for the universe. We don't know. In any case, the weak force first, the electromagnetic force second, then the strong force, then gravity. That's how the forces at time t equals 0 plus were presented somehow, had manifested themselves in ways that we can explain today. And for that, I found in a very interesting document that I have also added here, which I would like you to, because it's a very interesting one. It's relatively new, and I found it on Science. And I wanted to speak about the weak force, which we consider to be the first force that was, say, that was expressed, like at the moment the universe was created. So people think that at moment time t equals 0 plus, there was a group of neutrons, no charges, no activity, nothing. All right, at that moment somehow of time t equals 0 plus, there was something that was created, but it was inactive, a neutron. And the weak force, what did the weak force do? The weak force from a neutron was the reason for the creation of two particles, which are extremely important to us. One that has mass, and it's called proton, and the other that does not have mass, sometimes, well, usually now we know it doesn't, it's called an electron. And this one that is called the antineutrino is practically expressing a form of energy that leaves the neutron when that happens. And the weak force is always for a radioactive decay, all right? Which in fact you may have heard that a lot of times the way we find how an artifact was created like 1,000 years ago, 2,000 years, 10,000 years, is because of that. They measure, as a matter of fact, the radioactive decay in that. So the weak forces are responsible for that. Every time there is this split of from a neutron that is zero and it has zero charge to two opposite charges and equal, like in this particular case, in the simplistic version, which is one proton, one electron, that is, the weak force is responsible for that. But what happens when the weak force results in this, creates that? Immediately, from zero charge, we go to two equal charges and opposite. So what happens then? The presence of these two charges create what kind of a force? The electromagnetic force. All right, you have one positive charge, one negative charge. They are attracted through an electric source. If the charges are steady charges, of course, in this particular case, there was a very, it was velocity involved, all right, but a steady charge, a charge that remains the same place and it has the same value, and another charge which is the same but opposite, or opposite charges, they feel an attractive force. All right, so if you let them free, they will come together until they come together and create zero, if they could. So immediately after the first creation of protons and electrons, you see then the presence of an electromagnetic force. And in the beginning, people think, on the basis of this theory, that the weak forces and the electromagnetic forces were the first two forces that were manifested in this very short period of time. That we don't know how short it was, I mean, compared to our lifetime. Then what happens? Of course, there were many neutrons that went through this transition. So you went many protons that were especially in a small, because, well, you don't know how it was, all right? If you assume that all of this was happening in a small area, whatever that means, then you had a lot of these protons together, a lot of these electrons around them. There was like a conglomerate of all of these, but at very close distances. If there were only these two forces, then all of the protons will just be repelled. All the electrons will be repelled, and eventually the electrons will collapse with the protons, will go back to where they were. That did not happen. Why is that? Because the strong nuclear force manifested itself. And what happened? The protons that were so close together were attracted with this nuclear force. So the protons came together and created what? The nucleus. All right? And when the nuclei were created, some of them had more protons, others had fewer protons. The electrons then arranged themselves around them. But the strong electric force, the strong nuclear force, was much stronger in close distances than the electromagnetic force. So instead of repelling these, attracted the protons, and it was so much stronger so that protons could not be attracted by the electrons, all right? So the protons got together, and then the electrons arranged themselves around them. And then what happened? Then we had atoms, all right? Interesting. When atoms were created, then an atom has a mass, all right? Obviously, that's where you start having a mass in place. And then what happened? Then you have gravity forces that apply between masses, all right? And eventually brought, it was like all of these symbiosis of the four forces that arrange the atoms to come together, arrange themselves and create molecules. And molecules came together, arranged themselves and created, and eventually the first form of life was created like that. That's why we call it that. So I wanted you to have this kind of understanding. So you will see a lot of things written in the popular press. It's important for you to be able to place what you know, specifically what we will learn about electromagnetic forces in the context of everything else. Any questions about this? Okay. So now that we spoke about this, let me see, go back. We would like to speak at this moment about the force itself and then the field. So let me go back to the fundamental forces. And then forces, we understand now what a force is. In fact, we feel the force of gravity, all right? It's something that draws you. I mean, if for some reason this floor collapses, we're gonna all go down, all right, because of gravity. So the force applies on us, I mean, our weight. We carry that force with us, all right, because we feel the impact of the force, and this is our weight. Those of us who are bigger have more work to do. And then a little kid, for example, it's easier for a little baby to go around. It has less force to work against than an adult, all right? An average male has a more force to, that's why it develops a different physiology, more force to work against than an average female, all right? So that's how physiology changes, because of gravity has contributed so much. Because we feel it. The bottom line is all forces exert the same kind of feeling. All right, so gravity happens to be a force that expresses itself in the macro world. All right, the other forces, we don't feel them because why? Each one of us is made out of who knows how many molecules, and every molecule has in there who knows how many atoms, and every atom has a nucleus. I mean, and of course, we are in the macro world, all right? We cannot feel all of these forces in there. We cannot feel the force between our atoms, but we see the results of it. So the fact, as I said, that I'm sitting on this and I rest my feet on this floor is because of gravity. But what of the forces stops me from going through? Because in reality, if I wear a teeny camera that was like so small, like that I had the dimensions of the distances between the atoms, I could see holes because the floor is made out of molecules and atoms, and then the spaces between, I have to tell you also, the space, empty space between these entities is so huge that if we were to be as small, like say, as the nucleus, we could walk freely. It would be like another universe, all right? But we don't go through. Why is that? What force is it that stops us from moving through those holes? Yes, it's the electromagnetic force that keeps us in one shape. Otherwise, if for some reason, say something happens and this force disappears, we're all going to become particles in one split of a second. All right, so they are with us. And of course, we see them, unfortunately, like the nuclear, the strong nuclear force. You see it whenever you have a nuclear accident. I don't know whether you've seen the Chernobyl. Probably that happened before you guys were born. But it was a major incident. And that's what you see, this force, you know, it happened, there was this avalanche, you know, phenomenon that started small, and then eventually all of this material went through this. I mean, it breaks, what happens is it breaks the bonds between in the nucleus, between the protons, and that really results in a humongous amount of energy that is released. And of course, in form of heat and then all of this. But so we see that too, all right? And then we see also, as I said, the weak force from the radioactive decay that we measure in material. So they're all somehow part of our lives. And they were the reason for us being who we are. Now, from forces, however, so far so good, you can argue. The question is, why do we now talk about fields? Why do we not start with forces and then try to, you know, do all of our engineering and whatever we have to do, all of our designs in wireless circuits and everything, we do them using electromagnetic forces? Why is that? Because if you remember the electrostatic force, do you remember that from physics? We will do it also next week, but in the electrostatic force, it's a force that exerts on two charges, all right? It's a repelling force if the charges have the same sign. It's an attractive force if the charges have a negative sign. And how big the force is depends on the two charges, all right? So I am one charge, so many coulombs, another person is another charge. Depending on the force in between is going to depend on the charges. Now, a lot of times you want to, we call one of the charges like the source, and the other charge, we call it the observer, all right? So if I am a source, and then there is an observer that comes next to me, then both the source and the observer will feel that force. If I were to use this and then try to design something, it will get very complicated, because immediately, say if I try to design the source, me, immediately the observer becomes part of this equation. but we want our expressions to be independent of the observer, because I would like somehow to make my designs observer independent. So they apply to whatever observer comes around me. See, that's how we design sources. We don't, when I want to design a transmitter for this, the people who design them want to design the best communications transmitter. They don't say, oh, which receiver is going to connect with that so we can design it. Then you would have to know who is going to receive that and design it only for that transmitter and that receiver. Of course, that's not our. So we try to eliminate one of the charges from that concept. All right, we try to eliminate the observer, make it observer independent or observer agnostic, if you like. So if you go into this equation for the force, and we find that we call it the Coulomb's law, if you remember from physics, we are going to see it again quickly next time. Then we divide that force with the charge of the observer. When we do that, then we create a new entity, which is not force, because it's force divided by charge. All right, so obviously it's something else. Well, that new entity is independent of the observer, and we call it the field. Why is that important? Because if I know that if I am the source, I am a charge, that I'm sitting here, if I know the field that I create, then I can find the force on any observer that comes by multiplying that field by the charge of the observer. All right, so that gives me tremendous flexibility. So the field is not a real entity that we can observe, we can feel. It's a made up entity that is helping us to take real concepts and put them into design and do different things with that. All right, so that's why we introduce the field. A lot of times students would come and say, what is this field? Well, it's an entity that we have created, all right? Not that it did not exist in nature like the forces. It was an entity we created to be able to understand the forces and their impact and design around them. All right, so that is where the field is. Now, there is another thing that we want to remember, because a lot of times you're going to hear electric field, you're going to hear that. You're going to hear magnetic field, and you're going to hear electromagnetic. So let me ask you this. You have probably heard all of these terms. Are those similar or in nature, or they are different? What do you think? Yes. So let's then to be a little more careful. You're on the right path. Let me say that. But let me be a little more careful. So electric field, when we hear that alone, I mean electrostatic. So it's electrostatic, it's magnetostatic, and then it's electromagnetic. All right. So these three. So I think your argument stands correct that they're the same. They're not different, even for the electrostatic, the magnetostatic, and the electromagnetic. Even if historically we have separated them, because historically we observed the electrostatic first, then we observed magnetostatic, and then we observed electromagnetic. Came last, historically speaking, all right? So every time when people observed the electrostatic field, they thought that was it. When people observed the magnetostatic, they had no idea that it had any relationship with the electrostatic. So they developed the whole theory early on with that. And then when they observed electromagnetic, they did not know that this electromagnetic was somehow related to the other two until late. So it's for historic reasons, but in reality are the same. It's just that we observe them under different conditions. So let's start with to see why they are the same. If you want to see if fields, if forces or fields rather are the same, you ask your question, what generates them? In reality, when you say what generates something, you imply what generates the force. All right, this is, but we speak about fields, all right? So we don't have to worry about the observers. So you say, okay, what generates an electrostatic field? Do you remember? A charge, what charge? A static charge, a charge that remains constant in value and in space. All right, that creates a static field, which is called the electrostatic field. What creates the magnetostatic field? I hear like noise, but well, that's a pulse. Yeah, but what? So tell me a little more about. This is the poles are not the source. The poles are the observation, the result of our observation when the magnetostatic field starts and where it ends. But what is the source? It's a static current. But what is a static current? Charges, electrons, obviously, charges that move with a constant velocity. All right? Charges that move with a constant velocity create a magnetostatic field, but they are charges. It's just that they move with a constant velocity. Okay? Electromagnetic. What is the source? Yes. But with what? Move though with? Yes, they move, but with a change in velocity. Not constant, not constant velocity. The velocity changes over time. Increases, decreases, it changes. So all of these, the sources are charges. It's just in one case it's a charge that does not move and it's the same. The other time is a charge that moves with the same velocity, and the third time is a charge that moves with different velocities. The change, velocity that changes over time. So it's the same thing, all right? But we study them separately. And why is that? Because it's easier to start thinking of electrostatics because you isolate, all right? Then you start thinking of magnetostatics. And then you put the two together. It's easier, but there is no other reason we start that. And yet, there are very important applications that each of these fields have. So it's not just, so the fact that we study them separately allows them also to do some interesting things. So for example, from statics, we derive equations and design rules for digital circuits. We start going into electromagnetics when we want to either solve for circuits that are in the analog domain, so they do radiate, like communications. Of course, electromagnetics is very important. Or if we want to go to digital circuits and we are looking for parasitics. Parasitics is a big problem, all right, that a lot of times designers will have to deal with. So what we're going to do in this class is to learn about electrostatics, magnetostatics, and electromagnetics, but always with an eye on what kind of information this gives us to be able to do interesting things, right? So that's how we're gonna do it. Any questions about what we covered today? Maybe then I need to ask some questions myself. So how comfortable do you guys feel, and girls, about material that you can cover in other than vectors in coordinate systems? How far back did you do that? Cartesian, cylindrical, spherical, any transformations from one to another? Okay, so you guys have to revisit that a little bit. Keep it, just I would say, go to the book and just glance it through. Don't try to memorize everything, just know what it is so you can find it. And the other thing that we will need, but we will need it a little later, will be complex numbers. How far back did you have any complex numbers? Okay, good. All right, because we will need that to cover it in transmission, which is like electromagnetics, all right? Electric and magnetics. All right, perfect. Okay, so for this week, what I would like you to do is, remember, do the quiz, top hat, by Monday, just before this class. Do the homework, all right, which is due, it's only on the syllabus and it's due on Sunday at 6 p.m. And office hours are right after my class. So obviously today, I don't know who's gonna come for office hours, but email me if you wanna be, but starting this coming week, office hours are gonna always be online, right after the class from 3:30 to 5:30, Monday and Wednesday, and then on Sunday from 3:30 to 5:30. All right, in case you have any questions. Yes.
The top line assignment is due for grade, right?
Yeah, it has grades it automatically. Yes.
So I just wanted a little more explanation on the static and
Yes.
like the bearing changes. Can I use the one of the expos?
Yes, of course.
So for say like we have a magnetic base or an object that has magnetic properties. So like this magnet, right? So charges are just in their places, right? They're not transforming by.
I'll tell you what it is though. In this case, the charges are not like that.
Right.
But what we see here are in this one, the charges are not exactly steady, but they go on, they spin like this. And then here they spin over.
So enough of
So you know why? Because if you go like that, that happens all the time inside materials. But some materials, like the magnetic materials. So this one, let's assume the base like a small dipole. Yes. Here you have all the positives and here you get this in magnetic materials. Or otherwise they cannot move to mix up and cancel out. So this creates one magnetic field that goes like that. And then here,
Okay, all right, yeah, that explains a lot. And then also, since I'm a little crunch on time, I was wondering if you have like any experience with MRI machines or
Yes.
going over those topics.
I don't have that much experience with MRI machines, but if you are interested, I can ask a colleague of mine to come and give a give a lecture.
Yes, I love it. My name is Roman Alvo.
Okay, no, of course, yeah.
Nice to meet
Nice
you.
to meet you. Yes, that's a good idea. I'll ask you to come and give a lecture.
Sweet, thanks so much.
Okay,
I had a quick question
Yes.
about the homework.
Yeah.
So I did it after our first class. And there was a couple of questions about top hat,
yes.
stuff that I didn't have the answer to.
So go and resubmit it.
Resubmit it?
You can resubmit it an infinite number of times
Okay.
until the deadline.
Okay, thank you.
Yeah, sure.
You can ask your question first.
Yeah, so
Yeah.
sorry, I just switched from the 8 a.m. session. I thought this was at 2:20, so I was in Zoom outside watching the rest.
Oh,
of the
okay,
lecture,
well,
so I
that's all right.
I missed part of it.
But you do not miss really anything other than remember to do the top hat,
Okay.
which is
yeah,
the
so
same for both sections.
I already paid for it. Oh, it is the same for both sections.
Mhm.
Okay, cool. So if I just
Yeah.
do the quiz through there, I'll be
Yeah.
fine.
Uh-huh.
Okay, that was my only question. Thank you.
Sure.
I just had a question on the observer independent
Yes.
thing. I kind of got lost
Okay,
there.
so,
Um,
so here, for example, you have to chart this Q1. Let's assume that this is Q1, but I call it the Q source,
okay, Q source.
and then Q. Sorry. Uh, And then this is the second chart, I call that Q observer.
Okay, that's the Q source.
Yeah. So, let's assume that this is plus 5 microcoulombs,
Okay,
and this is minus 5 microcoulombs.
okay,
So the force in between the two is gonna be attractive force.
yeah,
All right. Now, this force is an electrostatic force, and it is Qs times Qo divided by 4 epsilon naught, the distance d.
okay,
So, if I were to work
Thank
with
you.
forces,
This is the quiz.
I would need to know not only the source, but every observer around it. So if the observer moves here, I would need to know the new position of the observer.
No. It's
So what I do, I develop the, so the force is a vector, all right? And it's like along this direction. I show it like that. That's the direction vector.
direction vector.
Yeah. We'll see that. I just want to explain to you right now.
Okay,
The electric field, we write as F sub B divided by QO.
Yeah, I remember you never said.
okay,
So the electric field is going to be only a function of Q sub S. So practically that tells me that if I have a source here, which is in only the source I want to know about, then this source is going to create around here an electric field. All right. And the electric field, if the source say is positive, usually, since we do not know what is going to be out there, we show that as like this.
okay,
Always starts from a positive.
okay,
All right, like here.
yeah,
So then it says that if this distance remain constant and every point along the circle, the force that another Q is going to come here, that Q is going to be the same around the circle. For that
oh,
Q.
okay,
All right.
okay,
But I don't need that Q to make that statement.
oh, you do,
See? So this is E. So when you look at the E,
oh, okay,
the only thing is that.
yeah, so all you really need is the source,
Yes,
the charge of the,
Yes.
the source.
the charge that forms the field.
Ah, I see, I see, I see. Okay, thank you very much. I
You're
will
welcome.
be writing all of this down.
Okay, no problem.
Okay.
Yes, yeah. So